Today we will go to discuss about an lecture video of solved problem of heat transfer in cylindrical problems. So in the given problem is a steel tube with 5 centimeter inner diameter, 7.6 centimeter outer diameter and thermal conductivity is 15 watt per meter degree Celsius is covered with an insulating covering of thickness of 2 centimeter and thermal conductivity 0.2 watt per meter degree Celsius and a hot gas at 330 degree Celsius with thermal coefficient is equal to 400 watt per meter square degree Celsius. Flows inside the tube, the outer surface of the insulation is exposed to the cooler at 30 degree Celsius with thermal coefficient H is equal to 60 watt per meter square degree Celsius. So calculate the heat loss from the tube to the air for 10 meter of the tube and the temperature drops resulting from the thermal resistance of the hot gas flow, the steel tube, the insulation layer and the outside of the air. So this is a given data of the problem, and here we indicated as the all given data through this diagram, and diameter 1 is equal to 0.05 meter and radius is 0.025 meter and diameter 2 is 0.076 meter and the radius is 0.038 meter. And the radius of R3 is equal to total outside radius from the inside is equal to RS plus thickness of insulation. Here is an R2 is equal to 0.38 and thickness of insulation is also given is 0.02. So the total radius of this cylindrical tube is 0.058 meter. And already given the thermal coefficients, heat transfer coefficient K1 and K2 are also given 15 and represented as 0.2. And inside and outside temperature is indicated as TA and TB is 330 degrees Celsius and 30 degrees Celsius. Both we converted into the Kelvin is adding 273. And the length of this tube is 10 meter and heat transfer local coefficient is 400 watt per meter square degree Celsius and 60 watt per meter square degree Celsius. So we need to find the heat loss Q and temperature drops and TA minus T1, T1 minus T2 and T2 minus T3 and T3 minus TB. Heat flow of this problem Q is equal to del T overall by R. Here is an del T is we know that inner minus outer TA minus TB and R of the cylindrical problem we consider from the heat transfer data book R is equal to 1 by 2 pi L and 1 by HA R1 plus 1 by K1 ln R2 by R1 plus 1 by K2 ln R3 by R2 plus 1 by K3 ln R4 by R3 plus 1 by HB by R4. So K3, K4 are not given. So from the above equation we neglect the K3 and K4 R4 term. So the final equation Q is equal to TA minus TB divided by 1 by 2 pi L into 1 by HA R1 plus 1 by K1 ln R2 by R1 plus 1 by K2 ln R3 by R2 plus 1 by HB R3. So the Q is equal to 7451.72 watt. So next we need to find all intermediate temperature of the cylindrical problem is Q is equal to TA minus T1 by TA and substitute this R is in resistance of the first part 1. The formula of the resistance is 1 by 2 pi L 1 by HA R1. So the intermediate temperature of TA minus T1 is equal to 118.59 Kelvin. Similarly, for we apply these both steps into the additional steps. So we go to the additional intermediate temperature T1 minus T2 and T2 minus T3 from Q off and intermediate temperature. And finally, we also get it out the equation of R of the resistance wall is equal to 1 by 2 pi L in 1 by K2 ln R3 by R2. Substituting these all values from the given data, we get it the intermediate temperature of T2 to T3. And similarly for that, we need to find the intermediate temperature of T3 and outside part. We substitute these heat transfer data values and RB of the resistance of the last part and the resistance of the last B part. This is the RB value 1 by 2 pi L in 1 by H3. Substituting these all values from this equation, we get it is T3 minus TP. So and final answer we get it of the Q and all intermediate temperature TA minus T1, T1 minus T2, T2 minus T3 and T3 minus TB. Thank you.